Okay. So thank you for the opportunity to speak here. My name is Vladimir Starostin. I'm a PhD candidate at Frank's group at the University of Tübingen. And my presentation is obviously a continuation of Frank's presentation. I'll go a bit into more technical details. And the topic of my presentation is the focus, let's say, is ambiguity, the phase problem that Frank already talked about, and how ambiguity affects reflectivity analysis, and in particular analysis with machine learning, right? So in this regard, I will first briefly talk about what Frank called the semi-pedestrian approach, the standard machine learning approach, which we call MLReflect 1.0. I will give you a brief recap and try to explain why it doesn't scale to high number of parameters, why it doesn't work with the more complex scenarios. And then I will try to explain how we can improve it with the updated version, which we call MLReflect 2.0, by using prior knowledge and incorporating prior knowledge directly into the machine learning pipeline. And still it has some problems that I will talk about. So to fully resolve these problems, to fully resolve ambiguity issue, we introduced the third iteration of our software, which we call MLReflows, which is based on normalizing flows technique, and we'll explain how it can speed up Bayesian analysis of reflectometry. So let's start with this first standard approach introduced by Frank, and show you why it doesn't scale to high number of parameters. To understand that, let's just look at how do we train it briefly. So in a nutshell, what we have to do is define some parameter space where we want our model to work on. I show you thickness and density. Of course, there are a lot of parameters with many layers that we can introduce here. And what we typically do is we generate some random parameter within this parameter space, which corresponds to some SLD profile. And then, of course, we can calculate the reflectivity curve based on this SLD profile. We can add some noise, and we provide this curve as an input to our neural network. And as an output, we expect it to return some parameters, which at the beginning are some random numbers. But what we do is we take the prediction error, the distance between the two parameters and the predicted parameters by the neural network, and we update our neural network to minimize this prediction error. And this is called backpropagation. I'm not going to talk about this, but the idea is that basically we show a lot of different examples, different curves within our parameter space to a neural network, and we train on it. So this is our training data. And what we expect to achieve here is, if everything goes well, basically the predictions will become closer and closer to our true parameters, and that will allow us to perform our reflectivity analysis with machine learning. But what can go wrong? And we know it actually goes wrong in this scenario, because if we increase number of parameters, at some point, machine learning stops working and gives us very bad predictions. And my argument is that what's going wrong is ambiguity, which Frank already introduced and everybody here knows, due to the phase problem. There are situations with different SLD profiles, different parameters correspond to the same or practically indistinguishable reflectivity curves. I show here some theoretical examples, but it gets much more severe if we take into account counting statistics or limited Q range, limited number of Q points. So of course, if we increase the number of parameters, we get more and more of these ambiguity examples. So if we take into account these ambiguity examples and we think about how it affects our training, so here is the two different parameters that correspond to basically the same reflectivity curve, right? And if we provide this reflectivity curve to the model, well, the model will have to give one prediction to basically one curve. And if we minimize the prediction error here, the prediction of the machine learning will appear somewhere in between of these parameters. And of course, this doesn't make any sense. It doesn't provide us any information about where the true parameters are, and therefore it fails. The question we might ask ourselves is, how does conventional methods, conventional fits, let's say, address this issue? And as we know, and as Frank already mentioned, that conventional fit relies on prior knowledge. We know a lot about our sample. We know the materials, we know the manufacturing conditions, we know physics, so we can narrow down this huge parameter space to some subspace with smaller ranges. We can fix some parameters, and hopefully within the smaller range, ambiguous results are outside our priors, outside our prior knowledge, and then we can fit it. The question is, can we use this idea with neural networks? And that leads us to this ML Reflect 2.0, right? So next iteration of our software with prior knowledge included into the pipeline. So how do we train this new updated neural network with priors included? It's very similar to the first one. So we have to define this large parameter space, but as the first step, we generate smaller random priors, these green boxes that reflect our knowledge about some certain sample. And then within these boxes, we generate parameters, and then it's exactly the same. We have the SLD profile and the corresponding relativity curve. We can apply some noise to that. And as an input to our neural network, along with the curve, we provide the information about our priors, right? The ranges within which we expect our prediction to be. And the model indeed gives us this prediction within the ranges. And then we can, same thing, minimize the prediction error, update our neural network, and hope that within this prediction ranges, this prior distribution, there are no ambiguity results. And we do that on many different scenarios. We show many different samples, like this training data contains of different priors with corresponding samples. And with this approach, well, from a user's perspective, it's basically very similar to conventional fit. We have a measured curve and we have the parameter ranges, right? So, and for some parameters, we don't know anything about them. We set higher ranges, and for other parameters, we can practically fix some of the parameters by providing very narrow ranges, and the model will give us the prediction within this defined parameter space. And actually, it works quite well, as Frank showed you some very complicated curves. So here I show some others. It tested, well, here I say up to 17. Actually, yeah, you can push it even further. You can push it even to 30, 40 parameters. And as you can see, the fit and the prediction and the input are very similar, and you can even improve it. So here there are no post-processing operations. You can even polish this result by applying gradient descent, and it works really fast. It's blazingly fast, basically milliseconds. But the main problem remaining is that if the ranges of our prior is wide enough to include ambiguity, machine learning will fail, as expected, as I already explained. But so will conventional fit, actually. And just to briefly demonstrate why we like basically all the conventional like approach where we just take one solution doesn't work in this case is, well, if we have two solutions within the priors, it's obvious that both solutions might be physically correct, and we would like to extract both of the solutions in our analysis. But all the machine learning methods that we discussed so far and conventional fits like differential evolution will give us only one result. And machine learning will be somewhere in the middle, and the fit will probably converge to one of the solutions, but will completely ignore the other one. So we need other methods to to extract all the solutions within our prior. And the most natural way, and actually increasingly popular way in reflectometry to address this, is Bayesian analysis. And we are coming to the third part, where I will present you the machine learning approach to Bayesian analysis of reflectometry. So just an idea, the sketch, how it works is basically, instead of getting one prediction, what you do is you generate samples from your normalizing flows. What it means is, basically, for those who use, let's say, Markov chain Monte Carlo, understands what I'm talking about, you are sampling from the parameter space, which is estimated, and then you basically get both of all the solutions within the prior knowledge. How do we train that? It's very similar to our previous standard models. We also generate these random priors and get the corresponding parameters and reflectometry. But here we have to estimate the whole parameter distribution within our priors, like the whole parameter space, which is called posterior. And to do so, the way we do that is we increase probability that our model gives in the two parameters. So we get the probability the two parameters, and we try to increase it with our model. And that's how we build up these distributions. So from a user perspective, it's bit different from a conventional fit, of course. When we have, say, our curve, here it's some simulated blue curve, but it can be experimental one, and we have some narrow parameter ranges. We know approximately where our solution is, and we try to generate the samples from the model, let's say 10,000 samples, and we get the solutions in orange, and we also get the corresponding curves which fit the input blue curve, right? But what if we don't know so much about our sample? If we widen up the parameter range, then the model, instead of failing as in previous cases, it will give us all of the solutions. It will give us all of these different branches of solutions that you can see here, and they might be really like a lot of them, right? And here's some gallery of complex scenarios on the left side with simulated data, and also some experimental data on the right side. And I will just briefly go through a very important topic, how accurate it is. So actually, it can be extremely accurate because we can couple it with conventional methods, either importance sampling or Markov in Monte Carlo. And as you can see here on the corner plot, we have this blue distribution given by the our normalizing flows, and then we can refine it in milliseconds. Actually, it's very fast. We can refine it to get the accurate distribution, which is basically the correct result. And you can do it with different methods, and they all match, as you can see. The question is, can normalizing flows miss any modes? This is the main problem here, because we can refine distribution, but if it's completely missed in some of the solutions, then we cannot do anything about that. But the great thing about normalizing flows is the way we train it, it guarantees revealing all the modes. So it can be wider than the correct solution, but not narrower. So by design, we basically obtain all of the solutions within the prior distribution. So here I show you practically the same example that Frank showed with our, let's say, semi-pedestrian approach, where we try to fit the in situ experimental data. And on the left, I show the results by our model with 3 open parameters: thickness, roughness, and density of the organic layer as a function of time. And you see there are 2 in situ data sets here. And we also can do that with conventional methods. I used here Monte Carlo importance sampling. And first of all, you can see that it fits really good. So basically, it gives the same results. Also, I show here the manual fit-where differential evolution, which doesn't fit very well because, as I said, it's not as reliable as probabilistic methods. And the interesting important fact is that this is a very simple data set, right? But we see, if we look at the third row with density, we see 2 branches, actually. We see the higher branch, which stops at some point, and the lower branch of the solutions, which seems to be correct one because it continues with time. And here we basically see the ambiguity in the data, even on a very simple data set with 3 open parameters. The question is, why don't we apply reliable conventional methods such as Monte Carlo importance sampling if we can, we can do that? The obvious answer is that with machine learning, we do basically exactly the same. We obtain the same results, but much faster. And the way how it's more efficient, I showed here, there is a metric called sample efficiency, basically how many reflectivity calculations are required to get the results. And for machine learning is orders of magnitude less reflectivity calculations required, which allows it to obtain the result in mere seconds. And if we think about this, it's only 3 open parameters. If we expand our solution to more open parameters, wider parameter ranges, the gain over conventional methods become extraordinarily large, and it succeeds 10 to the power of 10. So basically, it's mere second versus weeks if we want to really get reliable conventional analysis. Just before conclusion, I want to briefly sketch one kind of general idea. How can we use our Mallory flows approach to analyze reflectometry? So of course, we can obtain now all the possible solutions and ask ourselves if there's a unique single solution. And if it's yes, then excellent, we've done our analysis. But if it's no, if there are multiple solutions, then we can use different experimental techniques. We can measure more data, of course. We can use different contracts. We know how to do that. We can use co-refinement, and I didn't say about that, but we actually can do co-refinement with normalizing flows. And we can do that unless we have a single unique solution. So just to wrap it up, of course, as we all know, ambiguity is one of the main challenges of the reflectometry analysis. I try to show that it's both challenging for both standard machine learning and conventional methods. So here I present basically two methods, two novel machine learning methods. One is the lightweight approach. We call it Reflect 2.0. This is basically a fast alternative to conventional fit. It can be trained really fast, even during the beam time, and it works in complex scenarios, but only if priors are narrow enough. And sometimes it fails if we have ambiguity and we have no information about ambiguity in this case, right? And the comprehensive approach, which is among reflows, the normalizing flows-based technique, is the more, let's say, less lightweight solution, but it allows reliable and accurate real-time bias analysis by coupling with conventional methods, and achieves huge boost over sample efficiency boost over a conventional method. Well, the last point I actually didn't have time to present. We developed some PyTorch implementations of both reflectometry simulations and Markov chain Monte Carlo that speeds up a lot of things and can actually, it really helps developing all these methods. So yeah, thank you for your attention. And if you have any questions, I would be glad to answer them.